All right, so hi everyone. Welcome to the presentation of today. Today we have Luc Coupal, who is an intern in our lab for the summer. He just finished his bachelor's degree in computer science with the honorable mention of having done all of his master's lectures while doing his bachelor's, so it's quite impressive. And he's doing an internship in the lab with the goal of implementing a control algorithm, a very promising control algorithm on the Warthog, so we can do research with this algorithm. And his goal today is to give you guys a solid overview of his summer project.
You aim for how long?
What?
For how long is the presentation?
Should last around 45 minutes to 1 hour.
Okay.
Yesterday was 1:30, and we cut a lot of stuff. Yeah, around 45 minutes.
Okay, we'll aim at 45 minutes. That's good.
All right.
Go ahead.
Good luck.
All right. Thank you for the introduction. Yes, my name is Luc, and I'm very happy to be here today and to talk to you about what we're going to do this summer with the SNOW-AutoRally project. So let's do this. All right. So the SNOW-AutoRally project, what it is? Well, we're going to adapt the GeorgiaTech Autorally aggressive driving framework to the SNOW-AutoRally platform. Why we want to do this is because solving control problems subject to adverse conditions, which is the case with the GeorgiaTech Autorally, it's a key problem in mobile robotics. And how we're going to do this? Well, we're going to draw some insight from their framework, the literature, and that they publish, their implementation, and refactor it and adapt it to make it work on the Warthog and see how we can go beyond that. My name is Luc, like we said, and I'm working with Dominic this summer on this project here at SNOW-Lab. So everything revolves around this article. This article talks about very advanced topic in the intersection of stochastic optimal control and model-based reinforcement learning. It's full of very clever implementation detail. It's a gold mine. So it builds on top of multiple articles written by the same author in the year before they published this one. So my goal with this presentation is to give you a high-level intuition on this article. We won't dive in the detail because it would take all day, but my goal is to give you this sense of what's going on with this, what they do with this article and their implementation in AutoRally, and how we can relate this to the SNOW-AutoRally project. And like I said, we can go beyond with that. So, our ultimate goal, we want mobile robots robust in adversarial conditions. So, what does it mean being robust? Being robust is way more than just be physically strong or unbreakable. It's also about being able to make the right call when facing tough situations. It's about being able to land on your feet when you take hit, and it's about being resilient when you get knocked down. So if we want a robot to exhibit those kind of robust behavior in adversarial conditions, there is two decision-making problems that are critical to solve. So from a robot point of view, its representation of the real world is tested to its limit, and it starts to evolve in uncharted territory in those conditions. Many things become blurry, hard to assess, and unpredictable, making the task of choosing the optimal way to act a lot harder. And it's the same thing for humans, not just for robots. Take the guy on the left that is driving the car. At this point, it's not caring about the end of the race or what route is gonna take. He's just asking himself. He's just wondering what is gonna be his next move for the next millisecond, because the next action he's gonna take will make the difference between flipping his car and crashing it, or landing on its feet and maybe win the race later on. Um, so being robustness will require being able to handle those two problems that we see here. So this is the Byron-Booth triangle, and he presented this in a talk he gave at the LSS 2020, and what was interesting is that he talked about a different way to think about the robotic problem. Usually, it's control problem of solved in a model-based way, and but that's not the only way to solve control problem. You could learn them, or you can get insight from human expertise, which is the top. And what he's talking in this talk, what he presented in this talk is a way to frame the problem in a way that could use those other perspectives to get maybe new algorithm and stuff like that. So this is one of the algorithms we're going to see today. It's called model predictive control, and we will barely talk about reinforcement learning, which here, but the main where we are going is here. It's the information theoretic model predictive control, which do a little bit of all of those three. So a bit about Byron-Booth. This guy, the guy that presented that, is a director of the University of Washington Robot Learning Laboratory, and is a principal research scientist in the Seattle Robotic Lab at NVIDIA. So this guy work with robot, and in particular doing learning for robot and control. So I highly recommend this talk, by the way. So next step, part one, solving the sequential decision-making problem. So we're gonna try to build a way to communicate and talk about those ideas. And we'll start with this. So the sequential decision-making problem goes like this. This represents the real state, the real world, and you observe it. You don't have a perfect knowledge about it. You have a partial observation about it. And then you make action based on what you see, which lead you to a new state in the world that you observe, and you gain feedback whether what you did is right or wrong. So in our case, we're going to call this the cost function. How much it costed you to do that action in that state. So let's take an example. You're at the university in a corridor, and you're running. So it costs you this to run, and you see that in front of you there's a closed door. You decide to open the door. That's actually a new mate. It costs you this, and on the other side you see that there's another corridor, and you keep running, and you finally reach the cafeteria. So in the end, it costs you 3 times this plus this final cost. Now, let's check this other example. You're in the corridor, you run, it costs you this, but you see the closed door, and you decide to keep running. And the door is still closed, and you hit the door, you hurt yourself, you broke a leg, and now it costs you a lot because you end up in a wheelchair. So evidently, whoops, sorry, the decision, the sequence of decision that you make on the top is less costly than the one on the bottom, right? Okay, a little bit more formal. The notation will go like this. That's what we're going to use for the rest of the talk. So the real state would be represented by Y. The estimate state, which is your observation, will be noted X. And the control, the decision, we'll call this the controller or the control. This is the action you choose to make. It's going to be noted U. And the cost function, what is cost you to do this action, will be noted with a C. And when there's not the T stand for time step. So if we explicitly talk about one time step in particular, it's going to be noted with a number. Otherwise, it's going to be noted with the letter T. Now, yes. All right. Now, how do we know how can we think about X? This X would represent the system dynamic, but we don't have perfect knowledge about it because we're not God or a God. So we're going to have to figure out a way to think about it and to represent it. So this is called the model of the system dynamic. So what it is, it's the rule that could be represented as the rule that govern a universe. It could be the law of physics, the rule of the game. So it could be anything that can answer the question, if I do that, then this happens. So on the left side, you have the case of the deterministic dynamic, like is the case in chess. And on the right side, this is the case of stochastic dynamic, like it's the case, like an example for vehicle. What's the difference between those two? Like, except the fact that this is deterministic and this one is stochastic. Well, in the chess game, there's no unknown. The rule of the game won't change. There's a certain number of pieces you can move, and the piece move in a certain way. And when your king gets knocked down, you lose. Those are the rule of the game. And so they are deterministic. And on the case of stochastic dynamic, well, it stands for the many unknown that could happen on this dynamic. It's either because it's fundamentally stochastic, like rolling dice, Las Vegas environment, Las Vegas dynamic. You have this. This is by design stochastic rolling dice. But it could be also because there's thing you don't understand about the world, so you frame it as something that is stochastic, like some physics phenomenon that we don't yet understand perfectly. All right, about that. So in the case of robotics, it's usually end design. By domain expert and by system identification expert. So the knowledge about the expertise about a domain is really critical when you design a system dynamic model. So you're really you are depending on those experts and their knowledge when you want to do this approach. Okay, let's take a closer look under the hood what it looks like. For the robotic case of model robotic, a vehicle. This is the Ackerman vehicle model, and state would be represented like that. Here, the P are the vehicle body frame. This is the orientation, the rolling goal, the velocity. The last three are the velocity. The last one is the angular velocity, and they all represent stuff about the vehicle, how the vehicle is going sideways, the vehicle is going up a hill. All those things will change according to the state in which the vehicle is. So recap that ideally we thought that we need a model to know how to pass from one state to another, but there's a problem. What happens if, yes?
There is a question, sorry.
Yes.
So can you tell me again what is R? Because that's typically not what I'm seeing on those diagrams.
The roll angle, that's what I have.
That's right. It's the vehicle's roll angle. It's not the wheel radius or anything.
Okay, good. So that's more from the paper than from what you did before, right?
Exactly. Yes.
Okay, that's good.
For Acumen vehicles, it's one of the critical states they need to model.
Good. Good to me.
All right. Okay. So, like I said, we ideally need to know how to pass from one state to another, but there's a problem. So if we don't know, well, what happens if we can design a model that is close enough to reality? Or suppose that we don't have access to a reliable model. Could we learn one? The answer is yes, we could, either by supervised learning or by model-based RL. This is the approach we're going to see later on the presentation. Now, about optimal control. So there's two skills that are useful. The first one is being here. What can I predict about the future? And the other one is knowing what I can predict on the future about the future. What is the best decision I can make to have a minimum cost? So how do we do that? In the end, what we want to do is add this sequence of decision where we open the door before keeping running instead of crashing in the door. So, like I said, we want to find the optimal way to act. This will be called the optimal controller. We want U star, and we want to solve it. Find the sequence of decision that will minimize this, which is the sum of the cost. This is each cost, and this one here is the final cost, the final state cost. So we want to minimize this, and this is the optimization problem, and in the end, we're gonna end up with the optimal controller, the one that takes the optimal sequence of decision given its states. So this is how it looked like as a control loop. This is the controller. You receive your state. You take a decision which you send to your robot. You interact with the world, and you receive feedback from the real world, and you take consideration of what action you took, and you send a state estimate to the controller, which take another decision and go on until the end game. So there's two fundamental approaches to finding an optimal controller. The first one is planning, and the second one is learning. Planning requires a model of the system dynamic. Think about this. If you know the system dynamic, then you can predict the future. If you can predict the future, then you can choose an optimal way to act, right? So the next question, do we need a perfect dynamic model to do planning? Like we talked earlier, no, we just need a good enough one. Remember the quote, all models are wrong, but they are useful. That's the idea here. We do the same thing as human. We use what we know to move forward, and we damn well know that we don't know everything, and we might be wrong, but we still have to make decisions. The other approach is learning, which requires collecting sample or acquiring experience, doing interaction by trial and error. So the idea is that if you have access to a sufficient amount of data, and those data are a valid representation of the real world, then you can learn to act optimally. And the algorithm that we're going to see today do both. They do planning and they do learning. Okay, so what about the adversarial condition setting then? Recall that one critical problem we're facing is the reliability of our model when E is pushed to its limit. So the next question we can ask is there a control method that can work when the model becomes less reliable? And we'll see about that. We see one way. This is called model predictive control. And we'll start with this. This is a trajectory which is composed of the all state action sequence until the end that we took in the previous example. So you're in the initial state, you take an action that goes to the next state, you take another action until the end of the trajectory. So suppose your dynamic model F is reliable. Then we would only need the initial state x0 and a sequence of control U from 0 to the horizon t-1, so we can rewrite this as this. And you see that it becomes a recursive call to the with the dynamic function, which only take x0 at from start to finish. So assuming that you have a good enough model on which you can rely, you only need then x0 and your sequence of control from 0 to horizon n. So we're going to use this idea, and we're going to see one method of model predictive control that is called shooting. This goes like this. You fix the short-term horizon t. This is here. This is the m. Whoops. And you assume, like we say previously, that f is good enough for this horizon specifically. And then you take the action that you receive from your state estimator, and you set x0. You sample many sequence of control, and you choose an optimal trajectory from one of those sample sequence of control. You pick only the first. So you pick what you feel like is the optimal trajectory given those sequence, and you pick only the first step, the U0, this one, and you forget about the rest. And you send this one to the robot, and the loop goes on until you reach the end of your until you reach your end goal. So as a control loop, this goes like this. This is the mini sample of control that you took, and the idea is to find a way to choose the optimal U0 given all those samples you have, and committing to U0. So
there's a question
yes.
from Philip.
Yes.
So you talk about optimality.
Yes.
But I don't really see where is your equation. The cost you're minimizing is just a cost, or it's an error for following a trajectory. Right now, it's a bit foggy in my mind. What
Yeah,
exactly
no
you're
problem.
trying to?
At this point, it's going to be totally abstract, and we
Okay.
won't actually really talk about how it is specified. But there's two ways to think about it. From an optimal control perspective, this is designed by the engineer that will shape this cost function to help to make sure you act an optimal way that you as an engineer you desire. From a reinforcement learning perspective, the canonical case would be that this cost function is given by the environment. It's not designed, and you have to find a way, an optimal way to act with that in mind. Like if you were a baby with no supervision in a house, and that has to learn that touching oven when it's hot, it's not a good idea. And it has no parent. He's touch it, he's burn himself, he's gonna hurt, and that's the way the human body works, right? You have that feedback that you have no control over it. So there's really many ways to think about this, but from the optimal control perspective, this is designed by an expert with constraint in mind, with many things in mind, in the idea that minimizing this cost would lead to the optimal action you want.
Okay.
Is it yeah?
It's very high level because
Yeah.
when we talk about control, it's like here's a trajectory, follow it, and optimality is defined on the error between the two. In this case, it's probably going to be a bit of I guess reward shaping to include other things, but I'm willing to go at the high level so far.
Can I jump in for the const function just a bit?
Yeah.
The const function is proportional usually to two, and I think it's the case there to two main things. One is the error between the predicted pose of the robot and the desired trajectory. The second one is the commands you need to send to get there. So you try to minimize how fast you need to go to get to a point, and also how much of an error you have with the desired trajectory. So those are the two things you're going to try to minimize.
I guess there's an area of possible cost function in control. Could be collisions also, could be...
the collisions will be modeled as constraints to your cost function.
Okay, but not as a feedback, not as a... You cannot detect a collision and say that was a very high cost of...
I think maybe that's how they model it, but depending on the cost function, some of them will give a very high cost, some of them will not allow the function to go to the constraint.
Good. And also, in turn, I guess those are the typical symbols used, but if you go back one slide.
Yes. Whoops. Sure.
Yeah, okay. Mostly what triggered the question, and I was also thinking about cost functions because U star is your cost function, is your cost in the other equations, and here capital U.
Okay, no, maybe I was not. Just to clarify, U star is the optimal controller. The cost is there. This is the cost, and yeah, from paper to paper, there's many notation difference. I choose C in this case so that everybody keep in mind that there's a cost, but sometimes it's called L. In reward in reinforcement learning, it's R. And it's also fee when it's the terminal cost. So to frame it up at one thing, this is the cost. And maybe a high level way of thinking about the cost is it's a way to find optimality, but optimality is really subjective and it's really arbitrary. It's depending on what you want to do in the end, and it's also depending on how you think about optimality.
And here in that case, U star is the set of all control action that you want to do.
That are optimal.
That are optimal given the cost. Okay,
Yeah, because they minimize the cost. Yeah.
Okay, you can go for it.
All right. Talk about this. And we were there. Okay. So, all right. So MPC as one property that is really interesting is that the ability to anticipate the future events. And choose control action accordingly. As opposite to that, you would have the reactive control method type, like PID controller, that doesn't have that predictive ability. So we want that. And like we said, we want to find U star, the optimal way to act. So how do we pick this optimal behavior? In the case of a model predictive control, we know that we sample many sequence of action, and we need to find a way to choose which U0 is optimal given what we saw where is leading those sequence of action. So strategy number one, we could select the best sample action out of those, the one that minimize the cost. That could be okay, assuming that your dynamic model was perfect. But what would happen if our model was wrong? Then we would commit to an action that lead to, in reality, a sequence of action that will maybe crash the robot or something like that. So, okay, that's not really a good way a good strategy to find optimal behavior. Strategy number two, let's make an optimistic assumption about our dynamic model, and let's assume that he is more often right than wrong. Then could we make an average over those sample trajectory? That would solve the problem, right? But imagine the case where you need to avoid the tree. So you can go left or right of the tree. What would happen if we have an even number of samples that are going on the left side and an even number of samples that go on the right side?
You would average on the tree, so you would hit the tree.
Exactly. So we need something more clever to think about this this way, an optimal something more clever to think about how we find optimality in sequence, how we can pick this optimal behavior. So now about the GeorgiaTech Autorally solution. First, we want to find an optimal controller U star for a race car that can handle high speed on a dirt track. There's two main problems. The first one is that aggressive driving on dirt track push the reliability of non-modelization technique of the system dynamic to the limit of their breaking point. But the problem is that we need a reliable model in order to do planning, at least a good enough model to do that. And the second problem is that that adverse condition will expose the vehicle to many uncertainty, like signal noise, like malfunction, like premature wearing, loss of power, So this means that the intended control input UT will not necessarily be executed on the robot. So the signal that it's sent to the robot by the controller doesn't mean will be exactly that that will be input in the that will be act by the robot. So we need a controller that can account for this those two types of uncertainty. The one about the model and the one about the controller. So the main objective in the end is aggressive driving that optimize for wall clock speed. So we want to do the best clock on the best time on the racetrack, and what it requires is real-time control and fast control loop iteration. We don't have a full day to compute the next time step. It got to be solved really quickly. And we need it to be able to handle nonlinear dynamic, and we need to be able to solve stochastic optimal control problem. So, to return with the formal notation, we have uncertainty about which control will be sent to the robot and which control will be executed, which will affect the cost function and will affect the model, and we have uncertainty about the model. So we need a way to account from all those uncertainty. And their solution is to compose a dynamic model that is reliable in adverse conditions by using part of the system dynamic that we know that are reliable or easy to compute, and learn the other part that we have either less knowledge, that we're uncertain. We have uncertainty about how the state transition will work. And then do short-term replanning like predictive control, but with a twist about the way they think about optimality. And you do that every step of the way until the end of your end game. Okay. So now we need a way to build a dynamic model for those conditions. All right. So like I said, what they did is took the way they model the state and spot what is easy to define, and separate the part that we need to learn because it's that they are not because they are to assess, and they do this like that. This is the part that is going to be learned by a neural net. And how do you do that? Well, for learning, you need data, and in this case, we're interested in learning a transition function from state given action to next state in the context of aggressive driving condition. So to do that, they collect a data set of aggressive driving dynamic transition by recording expert demonstration. They did that by recording 13 minutes of driving data, composed of 5 types of maneuver: slow driving, zigzag, high acceleration, drifting, and high-speed driving. And all maneuver were performed clockwise and counterclockwise. And then they feed those data to a neural net and try to learn this dynamic model based on the action and the action that was took given that the state in which the car was in. So this was learned using a very basic neural net. It's a multi-layer perceptron with two fully connected hidden layer of 32 neurons each. By mini batch stochastic gradient descent with RMS prop. And even if it's a really simple model, it outperforms the other way to model the dynamic.
So a small question.
Yes.
Why not learning what is easy?
I'm sorry. Why the learning? Why the learning was this easy?
No, why they are not learning all the states? Why they split what was easy and what was not?
Okay. Well, if you take the full state space and you try to learn that, it's a lot harder problem that's trying to learn part of it. Plus, you know that you could do it. It's gonna be a lot harder to do and a lot longer to do. So if you do that, assuming you would like to do model-based RL, you're gonna slow down your step of learning your model. But in this case, what they choose to do is the following. Given that we have knowledge about the dynamical system work, because we have a year of study of math on the subject, so they're part of this state dynamic that we know well and we can model well. So why not use that? Use what we know that is reliable and learn the rest. So doing that, the search space for the neural net is a lot less complex. It's learn faster. And you could argue that maybe it's even more reliable because your learning, the final output is partially based on stuff that you know is reliable, that you can count on. So, and we do the same thing as human. We don't learn, I did not learn math, nobody learned math from scratch. I built my knowledge based on great mathematician from the past, and I build my knowledge on that. So no human start from scratch. If we would do that, learning the all state action space, it would be an analogy to learning from scratch. So that's the idea.
And in the specific case of their states,
yes,
what was
why those
easy?
Yeah, sorry. This part is the kinematic equation, which, oh, sorry, I'm going to go back. Yeah, I did not explain that. Yeah, why they split this like that? This part are the kinematic equation. So, like I said, it's trivial to compute, and but the other part is not.
X, py, theta, and roll, and the hard part is the velocity.
Yeah,
I can help with that. The easy part is px, py, and the orientation theta, not roll. Okay. And the dynamic part is from roll to the yaw rate, the theta dot. And why is it easy is because your entire state includes the velocity longitudinal and lateral in Vx, Vy, and the yaw rate. So from one state to another, if you know the velocity and the time step between two states, it's easy, it's trivial to compute the next position and orientation of the robot. So if you can identify all of the dynamic states, it becomes trivial to compute the kinematic states.
And why roll is not? So roll doesn't fit that.
The way they will use roll is not to do three-dimensional modeling, is to have another state in the dynamic equations. They will not identify how much roll displacement you will get with the robot. It's more like a parameter that will make it so the robot loses velocity as it's progressing. It's not a state that you will propagate to the next one.
Okay. Yep. Can resume.
Thanks. Yeah, so the key takeaway is just what we talked about the last few minutes. This is a quote from the Boston Dynamic Talk at NeuroX 2020, which I highly recommend too. They show their use of model predictive control, by the way, with a very good example in that. So this quote is, like they said in their talk, exploit everything you know, but don't assume you know everything. So that's the learning part. Next. Yeah, so like now, stochastic optimal control. How about sequential decision-making problem with uncertainty related to how the command will be executed? How do we find optimal controller then? Well, first of all, the objective, what we are going to try to minimize is not the same, because now we need to account for uncertainty. So now, instead of just adding the cost, we need to add this expectation, and we will redefine. Well, do I need to do that since we changed? Yeah. No, we'll go like that. Okay. Just keep this in mind, that we are now going to be taking into account uncertainty about the control, and this will be represented with this density function Q that I'll introduce here. So what it represents is the probability density function for an uncontrolled. For a control distribution Q, given the control U, and it represents the uncertainty that our control will have to deal when faced to adverse condition. So a sequence V will be a product of Gaussian V with mean UT, well, which is the controller that was sent to the robot. So this is our sequence of control, and this is the sequence of perturbed input Q given U. So we're going to use that for the way ETMPC is built. So their approach is based on both stochastic optimal control that we just showed and information theoretic control, which we won't have time to talk about, because it would take this would take the whole day. But it's really interesting stuff, and I'm just going to try to give you an intuition of how by using those two approach they managed to find a way to think about optimality. So first, we'll take the perspective of the car, the perspective of the robot. The green line here will be what we'll call the nominal control. It's a nominal control, or a nominal trajectory. It's the intended trajectory according to the current plan. Sorry. And the high level idea of the controller go like this. We sample many trajectory online, like we saw in the model predictive control. Then we adjust the plan, which is represented by the green line, the nominal control. And we take one step. We commit to the first action, U0, and then we replan. And on the right side, this is the robot here that is entering a corner, doing a cornering maneuver. And this is the abstract representation. You see in white, like I said, the sample trajectory, the sample mini trajectory, and the nominal control here in green. And you see that at every step, he's doing replanning and choosing the next time step that he is going to execute. So putting everything together with a control loop diagram, the intuition is the following. You take your nominal control, then you sample many sequence of perturbed control input. So doing that, you actually exploring the state action space. And then you're gonna find a way to reweight your nominal control based on those sampled perturbed sequence input. So it's not an average over trajectory rollout. It's trajectory sample we took. It's a reweighting of the nominal control U with respect to the expected optimality of the input sequences V. So the key idea is don't seek a global long-term plan. Just do short-term replanning like MPC. This way, your dynamic model can be a lot less perfect than normally would be required by other kind of optimal control method. You just need then a good enough short-sighted dynamic model that will work for this really short span horizon, and we can learn actually this good enough model based on expert demonstration.
I have a small question.
Sorry. Yes.
Typically, what is the time horizon in which they do their planning?
I don't recall for the article, but technically for MPC, it just has to be short time.
Okay, so
a few time step is in, could be a few seconds, could be a few milliseconds. In this case, it's a few
seconds.
It's 2 seconds in this case for AutoRally.
Okay.
So it depends on your case. But the longer your horizon is, the more uncertainty you add because your model is not 100% reliable.
Yeah.
So more you see in the future, more the gap between the two extreme here will be wider.
Mm-hmm.
Right?
And the rate at which they re-estimate all those trajectories, I guess it is really high. It's a high rate.
Yeah, in this case, yeah, it's high rate, and I don't recall the exact. Do you, Dom? Do you have? Do you recall this?
The re-optimization loop runs at 40 Hertz with their current platform.
Thank you.
Thank you, man. So yeah, so it's actually a reweighting, and when a little implementation detail that make a huge difference for them is to when they choose to commit to U0, given the reweighting, then they take the nominal. They keep in mind the nominal trajectory, and they send they forget about this one because they took that step, and all the other one are pushed back to the other one. So U3 will become U2, U2 will become U1, and U0 is the one we took. And they just have to sample one U nominal control. And this way, this is one of the tricks they use to be a lot faster and save compute time. All right, so experimental result now.
Another quick question. What happened if, so you gave the example of the tree. What happened if your distribution is multimodal?
Yes.
Are they handling that, or they just take
Yes, exactly. The idea is it's actually the way they're framing the optimality that is way different the way we think about optimality from a mathematical point of view. As we think of optimality in mathematics, usually it's about the optimum of a landscape. and there's only one global optimum. And in their case, they framing the problem of optimality in a way that account for this multimodal reality of the world. There's not only one way to reach an end game. You can take many paths. Actually, giving with the tree example, okay, left or right, but you could climb the tree and go over it if you are a Superman. So there's many ways to do the same thing, or you could instead of just go left, you can go far left. Or so there's many ways to act, and the way they're framing the problem give this capability of thinking about alternative behavior, and then instead of using just the optimal one that would be solved by gradient based method.
All right.
Actually, we decided to cut all part that about this idea because it's really deep and really. But I've written some stuff about that, and I'm gonna make them public. So if someone is interested, they can go into those maps and see those see this part.
That's okay. We are already 55 minutes in, and
oh damn,
we want to have a bit of questions from the
yes,
students.
all right. So experimental result. Whoops. Well, okay, it worked better than other method in aggressive driving setting. It's super fast, it's robust, but picture worth 1,000 words, and a movie is worth 1,000 more words. So I'll show you this. You see? Everyone seeing? Yep. All right. So in slow motion, you see that the terrain, the track is uneven. There are bumps, there are rocks. You see how the car is sliding, is drifting, and how he handle it. This one, you see how you saw the rock. You'll see the wheel go up in the air, and for a few, it's throwing off the car off track, but you recover from this. So you can see obviously that the car is able to handle a very difficult condition and recover when the thing goes wrong. All right. So quickly about this, they made multiple setting for their experiment. They went on at slow speed and ultimately high speed. That's I'm gonna show you. And they compared the algorithm with the baseline, another method, and they compare with other kind of method to model the model dynamic. But in the case of, I'm just going to see to show you this one with a target speed of 11 meters a second. This is going counterclockwise on the track, and this is going clockwise on the track. You see that the other approach of modeling the dynamic and the other approach of optimal control method did not work at all. And in a case of the baseline, he was only able to work on a counterclockwise setting. On the clockwise setting, it was too unreliable, and actually the success rate was so low that they had to stop making those experiments with this one. So in the end, what we can see is that indeed, yeah, ET MPC using a neural net is more reliable and more robust than the other technique. And we'll go with this. So how we can go beyond that? And how does it relate to SNOW, the SNOW project? Well, both aggressive driving and Nordic off-road driving will push the dynamic model to their limit. So both settings deal with the problem of modeling system dynamic in adversarial condition. So and also both settings require designing controller capable of dealing with uncertainty caused by noise, malfunction, wear down, power, loss of power, many things. And so lesson learned from one setting will surely help solving the other one. And but there's few limitations to their approach. And so recall that all design decision must be driven by their end game, their main goal. Sorry, this is the one with aggressive driving optimized for wall clock speed. So all design decisions they took and the many clever implementation detail they took are driven by this main objective. But SNOW has a different one. The main objective of SNOW is about robust driving, which means handling adversarial condition. But wall clock speed is just a bonus. So what if we took a different approach that optimized the AutoRally framework, algo, both for the design and the implementation detail, but in a robust, in a way that will be able to reach our end game. So there are many details in that me and Dominic have spot in the article and that could be a good way to do that. We'll talk about this later on during the summer. But framing the general idea for the difference between the AutoRally setting and the one we care about is this: in the AutoRally setting, it's a dirt track. They're doing loop, so they always going to pass on the same spot. Yeah, the dynamic, the environment is really hard, but there's some uncertainty that is not there that we do have to deal with in the SNOW setting of a Nordic condition. So the rally raid idea, like you see in this photo, the setting is that you won't go twice over a same spot, and choosing a wrong path could have disastrous consequence. It's not just about dealing with crashing with other car on the side of the track. Now, taking a road, making the wrong call on the path you're choosing could destroy your car. So, so that's it. Taking this into account, we have many ideas that we are going to try to do this summer with the SNOW with the Warthog. And so the first step the next step will be to refactor the AutoRally for the SNOW-AutoRally without changing the logic first, and then experiment and test, and then try other way, make it better, design and implement maybe the SNOW-Rally raid style, and then conquer the world. So that's it for me. Thanks for listening, and happy to answer a question you have.
All right, thanks a lot, Luc. Any question? For a matter of time, actually, we'll keep it one max per person. We'll start with Tommy.
I have a question about
We lose your sound.
Yeah.
Trop fort,
Yeah.
Alex, peux-tu ouvrir ton micro puis Tommy ferme le tien?
Ah, ben, je vais aller. Ouais.
Or Tommy, just ask the question to Dominic or Alexandre and he will repeat it.
It was about the prediction of the model. Like you have the distance, like or the time, like the 2 second step. That's cool. It can be like dependent to like the apex of the global planning and the speed of the vehicle. That's or this is fixed to.
Oh, okay, I understand. Could the horizon be a mobile horizon? Is this your question?
Yeah, and when the neural network is trained for it, you have a lot of dynamic, like a lot of speed and comportment at the same apex, or it's a fixed parameter, like the test that you have a lot of parameter to the test, or a small echelon of parameter.
You're talking about, okay, just wait a second, just to be sure.
Not the parameter, but the when they test the AutoRally.
Yeah.
Did you have a lot of scenario that he done, or it's just like 30 minutes of driving?
Ah, okay. Yeah, I understand. Yes. Okay. So is the do I have something about that? Okay, no. Yeah, sorry. Your question is about the I would say that the homogeneity of the data set. And the answer is, yeah, they have 5 types of maneuver that they recorded. So it's not an even, it's not an homogeneous data set with only one type of driving. The data set is divided into 5 parts, with some that are more slow speed, some that are more high speed, some that are that involve drifting, some that just try to capture the acceleration of the car. So in this way, the neural net will be exposed to a variety of maneuver, not of maneuver, but of dynamic in case of those maneuver, in the expectation that it will help better generalize when deployed on the track.
Okay, thanks.
My pleasure.
Okay, we have a question in the chat. Seems like the rate part is more high-level mission planning, devoid of dynamic aspects. The rate part depends on traversability. The rally part, ITMPC, assumes that it's always traversable. Any comments on that?
I would say that yeah, the rally rate there is more high-level planning involved, but if we forget about the high-level planning, it's still you cannot get away with choosing a short-term path that will throw you down a cliff, which is not the case on the track. The track setting, their wall, you just have to be in between those walls. So your short-term planning, it's constrained to that. In the rally rate setting, if we take that and put it in the rally rate setting, it won't work, because those constraints don't exist. You can go anywhere in the desert. So yeah, you have high-level planning, but other than that, the short-term planning still have to account to some stuff that are not exposed in this type of a racetrack on a closed track setting. Does it answer the question?
At a high level, just to make sure that the goal of the internship is to focus on testing on a track, and the long-term goal was more okay.
Yeah.
We extend that eventually to a race.
Yeah, where we can go from that after we have succeeded porting AutoRally to SNOW-AutoRally.
Also, if I can jump in, the algorithm assumes that your global planning is done. The ETMPC is not a global path planning algorithm. It will do your local path planning, so obstacle avoidance and control, but not the global path planning. So that still needs to be done by another algorithm.
Yeah. So Philip added that it feels like a lot of work. So indeed, the RAID part, let's consider that as a research direction in general, but we were super interested to see, even if we don't build a track, if we just use cones, so two traffic cones, and our map is just a single straight line that is an obstacle that the robot cannot cross, and we can loop around. Yeah. All right. Any other questions from?
Yes, I have a question.
Can you present yourself, so it might not be clear to look who we are?
Okay, it's Nassim from NORLab.
What are you working on?
I'm a PhD student at NORLab. I'm working on grasping with machine learning and deep learning.
Nice meeting you.
Yes, nice meeting you. Thank you for the good presentation.
Thank you.
My question is about the aggressiveness of the control. What is the difference between aggressive control and a control strategy where we could increase the rate or increase the number of samples, for example?
So the question is about whether aggressive driving is related to the rate of sample. Is that what you is that the question? Did I understand correctly, or?
Yeah.
Okay.
If I can rephrase, what's the advantage of using aggressiveness instead of like boosting a conventional strategy?
Yeah. Okay. So, so in that case, the problem they are facing is the fact that they're dealing with the uncertainty of the dynamic model. So their prediction of the future is highly affected by that. And the other thing is that we don't. They know that in this setting. Sending action you choose by your controller, sending them to the car will not necessarily be executed like we expected. So the problem is that the idea of their approach is how give them the possibility to deal with those uncertainty, and other kind of algorithms that are usually used and are a lot less complex solution are not able to handle that type of setting. And just to be the idea of aggressive driving is not the fact that you as a pilot you want to drive aggressively. It's the idea that when a driver push the car to its limit, then the way the world behave become highly uncertain, and the controller need a way to deal with this type of setting. So, to make the link with the SNOW platform, we're on Nordic condition. SNOW is we don't know perfectly SNOW the SNOW how it behave. Sometimes it's hard, sometimes it's melty, sometimes it's wet, sometimes it's I would say that it's thick, and so there are many uncertainty we had to deal with. Your truck can sink in the snow. So all those things are the idea that pushing what happened when we push our knowledge about the world to its limit, and how can we handle those conditions. So classic optimal control method don't work on their setting or don't work well. And with their idea, the way of using multiple tools that exist to put them together in a way that that is able to deal with those type of setting.
Okay, thank you for the explanation. And also, if I understand correctly, so the goal is really to push the system to be efficient. Is that compatible with, I believe, the goal of classic control to reach stability first?
Yeah, that one is more a question for Dominic than me. Oh, by the way, my background is in reinforcement learning. So you remember the triangle on the beginning? Yeah, I come from this church, and Dominic is come from this church. And right now we're trying, and we're both doing control problem. But I do it from this perspective. You do it from this perspective, and now we are walking and together to understand a way to solve those limiting when we push or a robot to their limits when we enter uncharted territory. So yeah, that your question with more for Dominic.
Optimality question. So the optimal control and the model predictive control notions or concepts are relatively new in the literature for mobile robots, but the notion of stability is also important for them. And since they are new, it's still an open question in research how you can have a completely robust and optimal model predictive controller. So we plan to use this, but it's not as developed as if you have, for example, a PID controller and you can really guarantee the stability. Those analyses are not there yet for model predictive control, but those techniques are much more robust or offer much better performance in the literature for mobile robots. So that's why we want to investigate them as well as other more classical approaches to path following.
Okay, thank you very much.
Thanks.
Nicola was in the list.
Yeah. Thanks for the presentation. I'm an electrical engineering intern at SNOW-Lab, and I'm just, I guess it follows what you were just talking about. But is this how you're going to approach the cost function with these techniques, and how is it related to the dynamic model?
Yeah, well, the first step, we're going to take the AutoRally platform as is and try to port it to the Warthog and fill in the blanks. Make sure that it works on it, and we'll try to recreate the setting that the condition that in which they use ETMPC, and then we'll add up some stuff like obstacle or more complex racetrack, and yeah, this is the plan for right now with where we're going with this. Yeah, and about the cost function, yes, there's some there will be some adaptation to do because their constraints are not the same. The thing we can do with the Warthog are not the same that they could do with their robot, and so yeah, there will be some engineering to do there. Yep.
Thank you.
I guess so. It's a work in progress, but you will have to think a lot about the experimental setup, because from what I recall, the AutoRally project, they crashed them a lot.
And without
which is less than something possible with the Warthog until Dominic built the cage that we can laugh about. But it's something that yeah, we are a bit more sensitive to crashing than the AutoRally setup, essentially. So
If I can
it
jump
was
in on
more a
that,
command than a question. Yep.
you're definitely right, and I completely agree. But as Luc kind of tried to talk about at the end of the presentation, they push the aggressive driving to the absolute limit. They go 11 meters per second, and it's super fast for a small car, and it's really impressive. But our goal is more to implement the algorithm in the Warthog, but we'll start at much lower speeds, and we probably won't even get to super high speeds. Our goal is to get the robot in like a steep slope or more different situations than having the robot go super high drift at super high speeds. And like Ackerman vehicles are really well designed to drift off-road. The skid steering vehicles are a little bit different in that regard. So you're right, and we will really have to think. I have a location on campus in mind to do those tests already, but for sure we'll be careful. But we won't be. Our goal is not to go in the aggressive driving spectrum. It's more to go in the many different off-road scenario spectrum.
All right. So Nassim is commenting on ANN. I guess it's neural network something.
Yeah, artificial neural network. Right. Oh, you
Okay.
see that?
It was a comment to Philip's comment.
Okay. 1/5 model, yeah. If we find those, we can use a marmot. That actually would be the closest that we don't mind.
Or Vol vehicle is the same remote
vehicle. Yeah.
control car.
Any other questions?
I have one. If Max doesn't have one.
Yeah, I have one question. So, it's about the input you took for the training of your neural network. Which type of input do you take? Because you need to take 1 or 2 seconds of data to predict your trajectory. So did you put all of that into your as input for the training?
Yeah, sorry.
Just to put into context, Luc didn't do anything yet.
No, not yet.
So he intends to use something.
It's more about the paper. So he was discussed about and what you want to do also.
Are you?
It's a great question, though.
Yeah. Are you asking about the learning part of the dynamic model, or you asking about the once learn, how is it deployed on and integrated with the controller?
I'm asking about the learning part. So after
the learning part,
the
all right.
data set.
Yeah. So for the learning part, in that case, they use single step sample. So they just use for the, oh, well, that's going to be better to use this one. Okay. They only use, it won't help this one either. All right, let's go with this one. They only feed xt, the state at the current time step, the action took at the current time step, and the next time step. They only feed that to the neural net. So given that, you learn how to generalize to other state action, next state dynamic. So in that case, they only feed single step, but that could have been multi-step sample. It could have been feeded, like say, a three-step sequence to the neural net. Could have been that. Actually, there are many ways to do this kind of learning for model-based reinforcement learning, which is an analog to this paper, but when in that case they only learn the model once offline prior to deployment, which in the case of a model-based ARL, they are relearning a new model at runtime by feeding them new sample that are took by the robot at runtime. So in this case, this is a single model learned prior with single time step data. So more or longer, it depends on the setting. It's really, and there's, in the paper, they found that it was good enough to just use single step, and it was helping actually, it was like less complex to learn. Because for the neural net, if you have to learn a more complex sequence of dynamic over, like we said, we took the example of 3 times step. Your problem is a lot more complex to search and find a good generalization than if you're only trying to learn with the really short-sighted approximation. So this is what they choose to do, but there's many more ways that could have been implemented, but this one was the one that worked for their setting, the one of racetrack driving, the one on and the necessity to go fast with the car. So yeah.
Okay. And do you plan to use these techniques for your for the snow?
Yeah, good question. We actually have many options on this, like I said, and the first step is analog. We'll do the AutoRally on snow, and then there's many other way there. You could there actually one better way to do for our case is to do ensemble method where with the neural net. So you took your data set that you with many various type of maneuver or context in it, and you use sub data set from this one, and you train different multiple neural nets on those subset, and then you do an ensemble on those and pick the right one at runtime. Which will be probably a better fit for us because we are going. If you change your setting a little bit, let's say, yeah, actually, hear this. Their setting, the way they train, it's gonna work for as long as the track doesn't change too much between what was learned. Based on the expert demonstration over 13 minutes, but versus if you run the track with the same expert for a whole day, the track will change. It's a dirt track, so they're gonna be all in the corner. They're gonna be the rock. The track will change its shape. So at this point, the model would be that they learn will be too far away from reality. Suppose we had snow on this. Just rain. It start to rain. The model won't work at this point. But if you use find a way to learn multiple model based on different track variation, the different setting, like add water to this, then your multiple model that will be deployed on the robot could give alternative option to the robot. Just pick the right model at runtime and go for this until it change. So this is one way that is done in model-based ARL to handle what is called distribution shift, I think. Yeah. Does it answer your question?
Can you add these external parameters, as you said, raining or snow, into your training, for instance?
Yeah, but each time, you could, yeah. And do you just need one model? Yeah, actually, exactly. No. That's the point. Actually, the model will learn a generalization over all of this. But if you use subset of this and train different model on each one will learn a good way based on that. Those subset, and then you took all those models and pick the right one at runtime. And whenever you need to change a model, use the other one. So this is the ensemble approach to. In model-based ARL, what they see is that this give the robot more versatility when the actual setting change. Instead of doing learning one single model that is optimal for his generalization of the whole spectrum of possible state action space problem.
Yep. Oh, okay. Thank you for your answer.
My pleasure.
Small questions. What sensors were used on the AutoRally, and what sensors do you intend to use on SNOW, in the SNOW project?
In good question. This one is not vision based. This one use a GPS for localization of racetrack boundaries. And the next evolution of this this article was using vision based instead of GPS for knowing where to go. So that's one add up. That's one thing that could be done. For the others, low level sensor report of the robot. This is more a question for Dominic than me.
But I think it's okay. I think you answered the question for what high-level sensors they use for localization, right, François? I think that's what you wanted to know.
Yeah, and the idea is that it's all of those sensors goes to the trivial part, or they are used to train, because we see in your neural net, it's the state that is getting in, and it's not the raw sensor that is getting in. So
yeah,
there's still some computation behind of computing the state of a robot based on noisy sensor is not that clear most of the time. So GPS, for example, is 2 Hertz, I think, or 10 Hertz. So it's super slow compared to the rate that the robot is moving. So there's many. I have the feeling that at the high level, it makes sense, but there's still a lot of noise getting in just building the state and then learning from those states. Do they talk about that in their paper, or they assume that they are able to recompose a good state?
Actually, there is multiple. Yeah, well, like this article is built on multiple other paper, and they just commit to one set of solution. But another paper they wrote like the year before was specifically about the learning model part, the model-based learning part. And in that one, they decompose the state in a different way. And they learn different parts of the dynamic model. So what I saw over those different papers that they wrote is that they try many different things. And so, like you said, they made some implementation choice at one point to try one that worked. In this context, we will have to adapt to our reality. But there's no one ground truth or one way to do this. Actually, it's very it depends on the problem that we are trying to learn with this neural net. Yeah. Does it answer the question? All right.
So, in terms of time, we're at an hour 40. I would be okay to stop it here unless there is a very important question or comment. I think we're all fine. All right.